Hey everyone, welcome. This is Tim Fox here, and I'm going to be leading the talk we have here on BERT shortly. Um, I wanted to just welcome everyone. We're going to be starting, of course, at 1 o'clock Eastern time. So that's going to be about 5 minutes from now. So Okay, so I want to welcome everyone again. So this is going to be a webinar here, and I am Tim Fox here from Elephant Scale, and the topic of today that we're going to be discussing is BERT, which is a revolutionary new model, which is developed by Google for the purposes of vectorization of natural language text. We're going to go ahead. I'm going to start my presentation here in a couple minutes. Okay, so BERT is stands for bidirectional encoder representations from transformers, and what it is. Here, let me go ahead and start the slideshow here. That's what it stands for. It comes from a white paper by Google. It was published last fall. And it was called BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding. So now this is a fairly recent white paper, but since this paper's publication, we've had an incredible amount of interest in BERT. And the reason why that is because BERT is, as a model, is able to achieve much better results than most things that we've seen before. Okay, so speaking of before, before BERT, there was Word2Vec. So Word2Vec, probably many of you are familiar with. It is also a Google-trained deep learning model. And what it's designed to do is develop a vector representation of a word. And it does this using a combination of several algorithms, a continuous bag of words, and skipgram. But what the result is it helps embed a lot of the meaning behind the language into that vector. And in fact, Word2Vec allows us to do a lot of vector operations to determine meaning. So for example, if we take the vector for the word king, and then we subtract the vector from the word man, and then we add the vector for the word woman, we end up with the vector representation of the word queen. So so that's pretty cool, because what's Word2Vec has done is that Google has developed a model which has been trained on a very large amount of data and able to embed a lot of the meaning of the words in that. So when we use that for machine learning, we're able to develop a representation for our text that embeds a lot of the meaning of the word there. So Word2Vec has been around now for a number of years, and it's achieved a lot of popularity, both in situations where we retrain Word2Vec on our own data set of natural language, or just using an out-of-the-box Word2Vec model. And in fact, GenSim library in Python, for example, has a very popular Word2Vec model, as does Apache Spark. So it's been pretty much embedded in a lot of places. Now, there's been a lot of follow-ons to Word2Vec, and namely one of which is a newer model called Elmo. In fact, BERT that we're going to talk about today really derives a lot of its ideas from, in fact, a couple earlier natural language models, one being ULM-FIT, and the other being Elmo. Now, in addition to those models, BERT is also based on also based on a model also pioneered at Google called the transformer. Now, what the transformer was originally developed for was for Google Translate. And so for Google Translate, what the transformer is it's a neural network model that's it's used for doing transformations of especially natural language data. And in fact, when you use Google Translate, what it does is it has a series of these transformer cells that then transforms your, say, English language text. So say if you're translating to French, then it has another series of transformer cells that has been trained to transform that intermediate data to French. So, this transformer model is actually something that's been pioneered by Google and used a lot within natural language. And so, actually the ULM, FIT, and ELMO models both depend on the transformer for doing what they do, as does BERT. So BERT is taking and building on top of those and expanding them. Now, let's talk about how we can use BERT for transfer learning. So what BERT is BERT is a model, and what it's been done is it's been trained on a data set of natural language text. Now, you can train BERT on any natural language data set, but a couple of the standard ones that are used is the Wikipedia data set, which is basically just a snapshot of pages from Wikipedia, as well as another data set which is commonly used, which is the I think it's the open book data set, right? Which has just basically a bunch of public domain and open source texts that are able to be used. Now, the way the model works for BERT is that we're going to take and do this with semi-supervised learning. So the way we do that is that we take just some text, but what we're not going to do is we're not going to train that with some kind of defined labels. Rather, what we're going to do is we're going to try to just train it with prediction of what the surrounding words of the text would be. So it's kind of like if I was to go to you and say, if I was going to take, say, a couple sentences of English text, and maybe if I was to black out one of the words of that text. Well, even though you may not know what that word is, you might be able to guess at what that word is based on the context. In fact, you know, if your friend is speaking to you and your friend is kind of searching for a word, it's like, what do you call that? Then you can probably say, oh, well, you must mean this. And because of based on the context, you can infer what you think that word should be. Well, that's basically what BERT does. BERT is, as we take in training, we're going to then use semi-supervised learning to help BERT be able to predict what the context is of the surrounding words. And the way that's going to work is we're just going to feed it such a massive amount of training data, you know. So and then now what that's going to be is we're going to have a transformed model of language that's going to be able to take in a text, and it's going to output a sequence of numbers. Okay, so what do we do with that sequence of numbers? Well, we can use that and apply it to, say, a given problem. So let's take kind of a simple problem that we might have. Let's say spam classification, right? So let's say we have a data set here. We have an email message like, buy these pills. And we could say, okay, that's spam. Or win cash prizes, spam. Or whatever, such and such is not spam, right? So now this is a common type of task that we might want to do with machine learning of text. Now I want to be clear, this isn't certainly the only place that we can use BERT. Actually, I mean, we can use BERT for pretty much any kind of natural language problem, and this one's a pretty simple one. But nevertheless, it kind of illustrates how we can use this for applying it to a real world problem. So the goal then is this is basically just a simple classifier. So we're going to say, okay, so this one is spam, this one is not spam, right? Or we'll say, for example, the answer here is to say 75% spam or 25% not spam, right? Okay. So the idea here then is, let's say we get the input. So the input here is say, help Prince Mayuko transfer huge inheritance, right? So you probably have gotten a spam email like that. So, so then what we're going to do is we're going to take that, we're going to do some pre-processing of the data. Then we're going to feed that through BERT. And BERT is going to generate a sequence of numbers that's going to represent the transformed version of that data. Then we'll use a classifier, and the classifier is basically just going to be a simple, fully connected feed-forward neural network, which will then take that and we'll do it through supervised learning, apply that to our problem, which is trying to predict whether it's spam or not spam, right? So the results here is that, okay, the email message here goes to spam or not spam. Now, there's actually a couple different versions of BERT. There's BERT base and there's BERT large. And they're basically very similar. In fact, what they involve is they involve using the modules of an encoder module, which is basically based on the encoder portion of the transformer that I referred to before. So it's a little bit like half of what Google Translate does, because Google Translate basically uses a transformer to do a bunch of encoder steps, and then uses another set of the transformer to do decoders. In this case, we're only interested in the encoder part. So we're taking and getting that, and then basically all BERT large is we just have more deep layers of the encoder, right? So that's the layers that we have. So what we're going to do is we're going to first take in our text sequence, right? So in this case, help Prince Mayuko or whatever. And what we're going to do is we're going to take a tokenized sequence of words. And those are going to be our input features. So in fact, there's some additional special tokens that we won't really go into. That CLS here, in this case, is actually one of those tokens, which basically just means that this is the beginning of our text, right? And so then help Prince Mayuko, etc. So these are going to be our text. And then BERT is going to be a pre-trained network, which is going to be based on a sequence of these transformers. And then the output is going to be a vector, basically just a vector in this case is just a sequence of numbers that's going to represent the transformed version of this natural language text. Okay, so let's go ahead now, and I'm going to show you an example of what we're going to see here. So okay, so give me a second. I'm going to load up a Jupyter notebook here that I'm going to illustrate this. Okay. All right. So so I have a Jupyter notebook here that I'm going to use to show us some code. Before I get to this, though, let me ask, from our participants here, if there are any questions so far about BERT. Okay, then let's go ahead and look at this then. Okay, so let's go ahead and look at some code. So, all right, so here we go. And let me also make this available here for you all to download as well. Yes, I just saw somebody that said that. So let me just go ahead and get this So give me a second here. I'll go ahead and get you a link that you can use to download this. Okay, so okay, so I'm just going to give you a link here that you can go ahead and download this. And I will also make the slides that I used available, the pictures and the slides available, as a PDF a little bit later. Okay, so there is that. Now, what I'm using actually to run this is I'm using something called Google Colaboratory, which is basically like a hosted version of Jupyter Notebook. So that's one option if you want to go ahead and run this. Otherwise, if you have a Python environment set up, say, for example, using Anaconda, you can definitely run this using Jupyter Notebook or Jupyter Lab there. So, okay. So let me go ahead and so, by the way, if any of you are unfamiliar with Colab, you can just do a search online for Google Colaboratory or Google Colab. And then what you can do is you can go ahead and upload this file that I just gave you to the Colab, your own Colab, and then it will go ahead and run that. Okay, so so let's go ahead and look at what our code is going to be doing here. So first of all, we are going to be looking at this using TensorFlow. And in fact, BERT as a model has been added to TF Hub. So if you're not familiar with what TF Hub is, TF Hub is a site set up actually by Google, and it's designed to showcase reusable TensorFlow modules. The idea being similar to something like GitHub or Docker Hub, right? So, so you can see here, the model we're going to be using is sorry about that. The model I'm going to be using here is this one, which is BERT. So, in fact, if I go ahead and browse that here, then we can search for BERT. Here we go. And I'm going to be using the BERT on the uncased corpus here. So this is going to be a deep bidirectional transformer trained on Wikipedia and book corpus. We talked about that before. And the details are defined in that white paper I showed you before about BERT. Okay, so actually one nice thing about this is that it shows us how to incorporate this BERT module using TF Hub in our own code. In fact, I can pretty much just cut and paste this code right here. Okay, now what I'm going to do is I'm going to be first of all loading my libraries here, namely TensorFlow, TF Hub, of course, and a few other things here as well. And also, there's actually a helper library that I'm going to be installing called BERT-TensorFlow. And basically, this is just a library this one here, which is a pip package that is going to help us in doing some pre-processing of our data, that kind of thing, to get it ready to run BERT. Okay, so what we're going to do is, what this is just going to say we're going to save this in a directory called model, and we're going to just save it as a local file rather than as a bucket or something like that. Okay, so first of all, I'm going to load some data here using it's actually data from Stanford, and it is the IMDb large movie review data set. So this is designed for a problem called sentiment analysis. And basically what that means is, can we tell whether a text is positive or negative in sentiment? So for example, this is about movie reviews. So if I have a movie review like, this movie is horrible, I hate it, then presumably we should be able to determine that was a negative sentiment, right? Or if this movie is awesome, it's the best ever, then that should be positive, right? Now, the problem is that in real life, text isn't always as simple as the examples that I gave you right there, right? So a lot of times when people talk about a movie, yes, they're letting you know their opinion, but they may be a bit more sophisticated than just like, that movie is good, or it is not good, it is bad, right? I mean, obviously, there's more subtle ways we can put those things. So, so that's why the sentiment analysis problem is a little bit probably more of a difficult problem than it might seem at first glance, right? Okay, so what we're going to do here is we're going to download this sentiment data and download it here. It looks like it's about 84 meg in terms of size. So if you're downloading it to your own computer, it might take a few minutes to download. Okay, so let's actually look at some of the data here when we load that. So we'll load this here in a pandas data frame, and we can see the first few words of kind of what it is. So it says, for example, I must say I was disappointed with this film, right? So, and it actually has two fields here. It has sentiment, which is a numeric number, looks like it's on a scale of 1 to 10. And then we have a polarity, which is just a binary 0 versus 1, which 0 means bad and 1 meaning good, right? So what we're going to be using actually in this is we're going to be using the polarity. So what we're going to try to do is we're going to try to see if we take the text and what the polarity, should it be 0, which means didn't like the movie, or 1, which means does like the movie. Okay, so again, our data column in this case is going to be this one, sentence here. And polarity is what we're going to be trying to predict here. We're going to try to predict whether it's negative or positive sentiment. Okay, and so we're specifying that here. Okay, now we need to do a little bit of pre-processing, and this is actually where that BERT TensorFlow library that we loaded with pip is going to help us. So what we're going to do is we're going to use that in order to convert the raw text into this input example type that will then be encoded the way that we're going to want to see as far as our BERT here. So in fact, we're going to go ahead and run this. And what that'll do is that'll give us a list of our input examples here. Okay. And we're going to do that both for our training data set and for our test data set. Now, like most situations where we have natural language, before we can really process the data, we need to do some basic pre-processing. And there's a lot of ways we can do that. BERT actually, the model, it turns out it also comes with some helper modules that will help us do this. So here's what we got to do. We got to first lowercase our text because we're using the BERT lowercase model. Now, we could also use a cased BERT model. And what that would do is that would treat the text as cased. But that does actually complicate things somewhat. So we're going to be using the lowercase model to keep things simple. So that means everything's going to get converted into lowercase. Now, we're also going to break it up into tokens, and that's called tokenizing. So for example, if we have text like Sally says hi, then that's going to break that up on word boundaries to say Sally says hi, right? So this is a very typical sort of step that we do when we're processing natural language. Now, after this, what we're going to do is we're going to break it into what we call word pieces. So now, words in English, in any language, for example, can have different ways that we have the word. Like, so say, for example, the word call. Well, the word call could be call, calls, called, calling, etc., right? So they're all basically based on the same stem of the verb call, but we can say that different ways. So what word pieces is going to do is it's going to break up that into two tokens. One for the stem of the word, so call in this case, but we don't want to throw away the grammatical context. So in this case, ing, that has some meaning that's useful for us. So what we're going to do is we're going to break that up into word pieces. So now the ing part will become part of the next token, right? So that's called word pieces. And then once we do that, we're going to map up our words into basically a dictionary. And that dictionary is going to be a vocab file. So when we pass things into BERT, instead of actually providing the word like call, what we'll do is we'll do a lookup index where the word call will be looked up as a word in the dictionary. So for example, call might end up as number, say 1, 2, 3, right? So then whenever we pass that in, it's going to be that number. And we're also going to set some special tokens like SEP and CLS. We won't really get into that, but that's kind of some special tokens that we can do that. So then what we'll do is we'll append the index and segment tokens to each input. Okay. Now, we don't really have to worry about most of these details because our data prep is going to do all that for us. So what we're going to do is we're going to then take the TensorFlow Hub module, and we're going to go ahead and create our tokenizer. So our tokenizer, what its job is going to do is going to take that and it's going to convert the raw text into basically a tokenized sequence of that will then be will then get our natural language text. So here's an example of what the tokenizer does. We have this text. This here's an example of using the BERT tokenizer. So you see here that we have each of our words here broken up into tokens, right? So, and you can see how that works. It's basically breaking up into words, but not just words only, because for example, you can see like suffixes like "iser" and stuff like that become a token in and of their own right. Okay, so then what we're going to do is we're going to now take and convert our raw text into this input features format. Okay, which is going to be tokenized. All right, so now that we have our raw text transformed, we're going to take and get our BERT model. So what we're going to do is we're going to take the TF Hub module here. TF Hub module is going to be so we're going to basically be using that, and we're using it pretty much as a black box, right? So we're just taking that from TF Hub. So we're going to give the link. It's going to be incorporating this BERT module here. We're going to be plugging in our BERT inputs, which is our output, our tokens, etc. And then we're going to be getting our outputs from BERT. Okay, now here's the thing though. The output of BERT, remember, is just a sequence of a bunch of numbers. In and of itself, it's not all that useful to us. Because our problem here is we're trying to find out a way to predict the sentiment. Now, the BERT outputs is going to be very useful for us in doing that, but we need to add something else. In fact, what we're going to do is we're going to add ourselves a fully connected neural network layer on the back end of this. And this is going to be something that we're going to train from scratch, not something we're going to be getting from a module or anything like that. Now, if you're familiar with TensorFlow, this is actually the low-level API. And so what we're going to be using is we're going to be adding a dropout layer for the purpose of overfitting. And then this mat-mul here is just going to be a single fully connected neural network layer. And then we're going to, at the end, add in a softmax layer at the end. Now, if you're not familiar with those terms like fully connected layers and softmax, this is basically just kind of a classical neural network classifier that we're doing here. The goal of this is we're going to take the output of the BERT module, which is just going to be a sequence of numbers, and then we're going to have a fully connected layer. And then at the end, we're going to make an output here which just has a single softmax output, which is basically, softmax is basically just going to tell us what's the probability that this is positive versus negative sentiment, right? And so that's what we're going to expect from the very end. We're going to be expecting this probability that we're trying to predict. And so in fact, it's going to give us a two numbers. And those numbers will basically be what's the probability that it's going to be positive sentiment, and then the second number will be what's the probability it's going to be negative sentiment. Actually, it's in reality, it's going to do those in reverse order. So first it'll give you the probability for negative and then positive. And of course, the fact that it has to be one or the other means that those two probabilities will then end up adding up to 1, right? So, okay, so that's what we have. So we basically, what this is, we have our basic BERT module. And then after that, we're adding a single fully connected neural network layer followed by a output softmax. And then that's the end. So that's what we have for our model. So what we're going to do is we're going to now do some training in TensorFlow. Now, well, the BERT module is already trained. So what we're going to do is we're going to take that BERT module and we're just going to incorporate that there. Then, however, our this final layer here is not going to be trained. So we're going to have to do a training on our data set in order to train the actual data for our problem. But luckily, we won't have to do much training on the BERT layers because that's already been trained. So what we're going to do is we're going to go ahead and we'll include some of our, so here what we're going to do is we're going to use the TF estimator API here. We're going to be using some hyperparameters here, batch size, learning rate. Epochs is going to be 3 epochs, so we're not really going to run it for very long because, you know, for the purposes of this demo, that's going to be, you know, 3 epochs will be enough in terms of the training time, although in real life, we probably would want to do more than that. All right, so now we're ready to go ahead and train. So what we're going to do is we'll go ahead and create an input function. And then what we're going to do is we're going to call our estimator and say .train. And then what we're going to do is we're going to take our input and run it for our, you know, we can remember our training steps was going to be 3. And we're going to go ahead and run that. Now, when you run this on Colab using a GPU, this will take us, you know, about 13 minutes. So for the sake of time, I just went ahead and ran this prior to starting this webinar. But if we were going to run this, we can just hit play. And if you run it on Google Colab using the GPU runtime, take you about 13 minutes or so. So that's, go ahead and run that. If you're running this at home, again, on your own machine, it will be probably longer if you don't have a GPU. So, so your mileage may vary on that. So, okay. So, what we're going to then do is we're going to go ahead and look at our results. Now, we got several different ways of evaluating the model. Probably the simplest one to understand is the accuracy. So the accuracy in this case is 86%. So that means is that 86% of the time we were right, and the rest of the time we were wrong. So now, normally with machine learning in general, we normally want to try to look at some different metrics. So here we have, for example, the AUC, which is the area under the ROC curve, and the F1 score. So, so these are precision and recall, for example. Now, what we see here is that I'm not going to go into kind of what all of those mean specifically, but what those kind of tell us is that, you know, the AUC, precision, recall, et cetera, those are all roughly the same. So what that tells us is that we can be pretty reliable that, you know, given some text, we're going to be right on this about 86% of the time. Now, that's probably, we could probably do better on that, let me just say. One thing is that we only trained for 3 epochs, which, you know, we could probably do better on that. The other thing is that we also did only one layer on the, one fully connected layer on the back end. And, you know, there's no reason why we couldn't have additional layers and that kind of thing. So again, all those things are things that we could certainly do. But let's go ahead and try this. So for example, we're going to go ahead and run our now trained model to get our prediction. So here we have some predicted sentences here. So for example, that movie was absolutely awful, right? Or the acting was a bit lacking. So both of those you would guess it should probably be negative sentiment, right? And then, so the film was creative and surprising and absolutely fantastic. So those two reviews you'd think should be positive. So let's go ahead and then look at what we have here. So we're going to go ahead and take our model, and we're going to go ahead, and hopefully I haven't timed out or anything like that. Yeah, there we go. So, okay, so you see, it only took a couple seconds for me to actually run the model. And that's because I didn't have to go ahead and retrain it from scratch. I'm just going ahead and feeding the data through the already trained model. So you can see what we got here is that movie was absolutely awful. Now, what we're getting here is we're returning the probability that it's negative and the probability that it's positive. So now, actually, what we have here is actually not the actual probability, but just the output of the logits. So I'm sorry, actually. So what we're going to do is we're going to choose the larger of these two values. So in this case, you can see here that so what we're seeing here is that this is showing us that the review here is negative. So in other words, we're selecting here so what we have here is that this is going to be right here, negative, and this is positive. Now, in this case, both of these are negative numbers, but we're just going to choose the larger of the two outputs. So in this case, the larger of the two is in the 0th position. So that means is that we're more probable that it is negative, and that's what we correctly selected negative. And then these two, you can see here, it correctly selects positive based on the output there. So, okay, so that's basically it. So now the focus here is not really so much on the classification step, which is basically just a very textbook kind of standard neural network, but rather the BERT module. And so the BERT module, of course, is, there's a lot going on in there. But the BERT module, of course, is we can use this for any kind of pretty much natural language problem. So we can take BERT, we can even use it as a black box if we don't really understand everything. There's no real reason why you need to understand everything at a really deep level. But you can take that and use it to what we call vectorize your natural language text. And then you can use that as a first step for then applying that to whatever problem that you might want to do, like text classification, like we did in this case, or for example, kind of document similarity, or topic discovery, or many other, or recommendation, or many other kinds of machine learning models that we can do. But BERT is going to help those machine learning modules work a lot better than if you were going to use something like Word2Vec or TF-IDF or some kind of earlier type of natural language model. Okay, so that is really all I had prepared here. So I wanted to then now allow attendees to ask questions here on this. So. Okay, sure. Now, okay, so got a couple questions. Let me address them first. So we had someone ask about retraining. So when we loaded the model, what we did here was we loaded the BERT module, and we specified it trainable as true. So what that means here is that we're going to load the weights for BERT but we are going to allow the optimizer, when we do training, in order to modify those weights. Now, this is a process called fine-tuning, which basically means is that we've already loaded the weights, and we don't really expect they're going to change too much, but we're going to then make those available for our training steps. Now, the fact that we're only training for 3 epochs here just kind of virtually guarantees that we're not going to be doing too much changes of those. But nonetheless, now, one option we could have done is we could have said trainable equals false here, which means that we wouldn't be, that we would not have trained the BERT layers at all. That's actually, though, a reasonable thing to do in some cases, because in that case, our training would focus only on training our layers and keeping the BERT layers as they are, right? So, however, if we have enough kind of time and GPU C/CPU power to run, then probably by allowing us to do retraining, we should be able to get better results for this problem. So, now, does that answer your question, Peter? Okay. Now, somebody else also asked is that how do we decide whether the language is positive or negative? Now, this is a supervised machine learning problem that we're dealing with here. So what that means is that we've gotten a data set here which has both the sentiment and the polarity already encountered here. I think how that data was generated is because on IMDb, the site, people typed in the text, but they also typed in a score for the film. So that's been included with the data. Now, the polarity, I believe, is just generated from the sentiment, and I believe it's actually just done by setting a threshold. So, for example, if it's 5 or under, then I believe it's set to be negative, and if it's over that, then it's set to be positive, right? And so that's where that's generated from. So actually, not necessarily, right? So presumably, if it says great, then it probably would be positive, but that's actually something that we're trying to train. So we're trying to learn those inferences based on the text, right? So we could, so that's the data. Now, dealing with bias in the data set, we're dealing with subjectively labeled data that's based on people's own, their own subjective criteria, right? So, so somebody, for example, might have rated things a different way. Now, in this data set, we're not really doing any normalization of the data, which in a real life scenario, especially if we were going to use the sentiment score, we might want to try to normalize our data based on that. But right now, we're just using the raw data. So, yeah. So yeah, but going on the last question about if it has great in the language. Well, now I want to point out though is that we're doing this based on inference, not based on kind of a top-down approach. So yes, the presence of the word great might very well, we might very well learn in a relationship based on that. But we are not, again, that's something we're going to be inferring from the data through the process of training. It's not something that we're going to be drilling down as part from a top-down perspective there. And in fact, there may be other things as well that may very well lead us to positive or negative. So. Good questions. Any other questions? Absolutely, yeah. So so asking about, can we use BERT for NLU, natural language understanding problems? And we definitely can use BERT for that purpose. So in fact, BERT has an example uh, that you can look at where they use the, so this is basically using BERT for a simple classification problem. But you can look at in their BERT, they show an example of using BERT for the SQUAD data set. SQUAD stands for the Stanford Question Answering Analysis, I think a data set. I don't remember the exact acronym. But so it's trying to solve a different kind of problem, which is closer to the NLU problem that you're talking about, which is a question answering problem data set, right? And so that's going to be a semi-supervised rather than supervised approach. So that is again, the supervised approach that we saw here for this classification problem is a simple example and I chose it because it makes for a good introduction. But certainly for more complex natural language understanding problems, we definitely can use BERT as part of our pipeline. So, okay, so let me go ahead and give a link here for let me go ahead and give a link about what I just talked about, which is talking about a paper here on BERT for question answering on SQUAD 2.0. So that should give you an example of that. So okay, let me also get a so let me see. About Peter also asked a question about explainable AI. So explainable AI is certainly definitely a hot topic, and what we're seeing with one of the things about any kind of deep learning, which of certain BERT certainly fits in that category, is that it's often difficult to try to explain why we get the results that we get, right? So and so out of the box, BERT is going to fit in that category of unexplainable AI, right? In other words, it's getting good result for us, but sometimes it's hard to try to determine exactly why we're getting those the results that we are. So that kind of, I guess I'd say that that certainly there's a lot of work being done in order to try to use models like BERT in explainable fashion, but that's kind of a pretty complex topic in and of itself. Yeah, I probably have to defer that conversation there. But just to point out that it is an issue, and it's something that it's something that that is worth is worth pursuing. So. Other questions? That's not something I've really worked on heavily. One of the criticisms of neural networks and deep learning in general is the fact that, it's not very explainable. And so one reason why some people prefer other methods like, for example, uh, 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 kind of decision tree type of approaches like gradient boosted machines, et cetera, is because the results for those are pretty explainable. So that is one of the criticisms of deep learning in general. But there's also a lot of work to try to resolve that problem. It's not something I've particularly worked on, though. So. Sure, I'll definitely do that. We didn't have very many slides, but what I'm going to do is I'm going to export those, and I'm going to go ahead and give you guys a link for that. So let me go ahead and do that here. Okay, there's the slides. As for the recording, I don't, again, that'll be something I'll have to get after the fact, but we'll try to do that. So. Okay. Well, thanks everyone so much for your great questions and everything. I hope to get a hope to hope that this is helpful to you and that you all were able to gain some good understanding of BERT and natural language processing using deep learning. So great. All right. Thanks everyone. As for emailing the slides, I'm going to get with one of my assistants. Actually, I think I don't, but I'll try to. I think we have the email list. I'll try to make that happen. Yeah. So. Okay.